Hi everybody and welcome to this last section of videos about limits and continuity. So what we'll cover now is infinite limits, vertical and horizontal asymptotes, and then we'll move on to limit laws and continuity. So let's start with infinite limits, and infinite limits are maybe easiest to explain with an example. So let's compute the limit for x going to 0 of 1 over x squared. And we haven't really seen this, but you can do this in two ways. So if we look at some values, so if we take, for instance, x is equal to 1 over 10, x is 1 over 100, and we let this go closer and closer to 0, what we have is that f of x, that's 110 squared, 1 over that, so that's 100. F of x for x100 is 10,000, and so on. So you see that if x goes to 0, f of x keeps growing without value. You can also see this from the graph. If we draw this function, then we see that as x gets closer and closer, the function values continue to grow like this. And that holds true both on the negative and the positive side. The function grows without bound if x gets closer and closer to 0. So here we will say that the limit is plus infinity, and this is a little bit tricky, so this you have to keep in mind, this is not a real number, but it just means that f of x grows without bound, becomes more and more positive if x approaches 0. Another example that we can see along the same vein is if we take our natural logarithm and we let x go to 0 from the positive side. Here we know that the graph looks like this. So the logarithm always goes through the point 1 on the x-axis and then becomes more and more negative and continues like this. So here, if we let x get smaller and smaller, then what we see is that the logarithm becomes more and more negative, and here we say that the limit is equal to minus infinity. So again, grows without bound, but becomes more and more negative when x goes to 0 from the positive side. And so we can summarize that by saying infinite limits are basically what you get if as x goes to a certain value a, the values of f of x get arbitrarily large, and here they can become arbitrarily positively large or negatively. And the first we denote by plus infinity and the second by negative infinity. Wrap this up. So this was 1, 2, and now we have example 3. So sometimes you have to do some manipulations. You already are familiar with this. So let's calculate the limit of x going to 0. of 1 over x squared minus 1 over x. And so here, a small trick that you can use. It's always a good idea to substitute the value x0 in there and see if the value makes sense. But if we do that, we get 1 over 0, that's more or less infinity, minus 1 over 0, that's also infinity. Get something that looks like infinity minus infinity doesn't really make sense. So the handy-wavy approach here doesn't work, or the intuition at least doesn't work. But what we can do is we can bring this on the same denominator to get limit of 1 minus x divided by x squared, x going to 0. And now what we see is in the numerator, if x goes to 0, the numerator goes to 1, and the denominator, if x goes to 0, this goes to 0. So we're sort of looking at something that's like 1 over 0, which is infinity, and we can already conclude from that that our answer is going to be one of the forms of infinity, but we still have to decide, is it plus infinity or minus infinity. If you don't follow this handy-wavy reasoning that I just sketched, you can plug in some values. For instance, if you plug in 1 over 10 and then calculate what this is, you'll see that the whole function grows without bound, so that's why we say it's infinity. But we have to think a little bit careful about, does it go to the positive side or the negative side? And here what we'll do is we'll make a sign chart. And so for the sign chart, we'll put the numerator and the denominator, and then we'll put the values that make either go to 0. So we get x is 0 and x is 1. And then here down below, we put the quotient, like so. So here, for the numerator, we have that 1 is 0, and then here we have plus, plus, plus. The function is positive here and negative here. And x squared is 0 for x is 0, and then is positive, 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 positive. And for the quotient, what we get is, for x0, we're dividing by 0 here, at x squared, so the function is not defined. It's positive for x less than 0, positive for x between 0 and 1, 0, and then negative. And in particular, if we look here on the right hand side, so, sorry, what I meant to say was, if we look here around 0, we see that the function is positive. So from that we can decide that if we go towards 0 from either side, we stay in the positive range, so the limit is plus infinity. And in fact, you can draw this function. It's a little tricky to do so, but you can, for instance, ask Wolfram Alpha to help you with that, and you get something like this. So it goes to infinity for x is equal to 0, crosses the x-axis, and then continues like that. This calculation with the sign chart is very good if you have an expression like what we have here, where you have something that's of the form a over 0, with a itself not 0, then use a sign chart to determine whether it's plus infinity or minus infinity. So closely related to infinite limits is the notion of vertical asymptotes. And here we can start with the definition. So the line x is a vertical asymptote if at least one of the following is true. So either the limit for x going to a minus of f of x is either plus infinity or minus infinity, or limit for a plus of f of x is plus or minus infinity. And here I should say it's a vertical asymptote of the function f of x. So for example, if we again take our function y is equal to the natural logarithm of x, we know the graph looks like this. We just drew it. And so here we see that the limit for x going to 0 from the positive side of ln of x is minus infinity. So x is 0 is a vertical asymptote. And x is 0, that's precisely the y-axis. So that's this line right here. So vertical asymptote you can think of as a vertical line, and the function reaches out to that line, but it never touches or crosses that line. So it gets closer and closer to that line without ever touching it. It's a bit hard to draw, but the gap sort of becomes closer and closer without ever becoming 0. So another example is y is equal to the tangent of x. So here we know that the graph looks like this with pi periodicity. And so what we have is for pi over 2, for minus pi over 2, and then again with periodicity here for 3 pi over 2. So in each case we see that, and let's write it out, for instance, the limit as x goes to pi over 2 from the negative side of tan x, that's plus infinity. The limit for x going to minus pi over 2 from the positive side, that's negative infinity, and then so on. So what you see is that all of these green lines are all vertical asymptotes. And again we have the same interpretation, so that the function sort of gets closer and closer to these lines without ever reaching them. So we have x is pi over 2 plus k times pi, with k an integer. So let's do maybe one more example. Let's look for vertical asymptotes of the function absolute value of x minus 1 divided by x squared minus 3x plus 2. So the denominator is a quadratic function, so I'm going to factor that. and I get x minus 1, x plus 2, x minus 2. And now a very good heuristic to look for vertical asymptotes. So here we want to find all vertical asymptotes. A good heuristic is to look for zeros of the denominator that are not zeros of the numerator. Because we want that limit to go to plus or minus infinity, and that is something that happens when the denominator becomes 0 without the numerator becoming 0. So here we have x is equal to 1 and x is equal to 2. Those are both zeros of the denominator, but x is 1 is not going to be a vertical asymptote because it's also a 0 of the numerator. By contrast, x is 2 is a 0 of the denominator, but not of the numerator, so that's going to give rise to a vertical asymptote. And we can see that a bit closer from the function prescription. So we had absolute value x minus 1 divided by x minus 1. So we can simplify that to say, well, this function is going to be x minus 2 with a minus sign for x is less than 1, and plus x minus 2 for x bigger than 1. And that means we can more or less draw this function. So the graph becomes, there's going to be interesting things happening at 1 and also at 2. And at 2 we get a vertical asymptote like this. The function going like that. And between 1 and 2 we have this branch, and then for x is less than 1 we have another branch like that. And the function is not defined at x is equal to 1. So here you see interesting things happen around x is 1, but no vertical asymptote. So the rule here to keep in mind one more time is to look for zeros of the denominator that are not zeros of the numerator.